And now that we've formalized the process of sketching the graph of a function by listing all of the things that we want to include in the function, let's take a look at our next example. Examine the function f of x equals x squared minus 4 over x squared plus 4 for the following properties and use that info to sketch a graph. So we want the domain, the intercepts, any symmetry, the asymptotes, the intervals of increase and decrease, the local maximum and minimum values, and the concavity and points of inflection. So if we want to look at the domain, we have a rational function here, and a rational function is defined so long as the denominator is not equal to 0. But this denominator is always positive. It's never going to equal 0, so we don't have any problems with our domain, which means our domain is all real numbers. So from negative infinity to positive infinity. As far as the intercepts go, remember the y-intercept we get when we set x equal to 0. When we do that in our function, we get negative 4 over positive 4, which is negative 1. So the y-intercept is going to be at 0, negative 1. For the x-intercepts, that's going to be when the numerator equals 0. So we've got to set x squared minus 4 equal to 0. And if we do that, we're going to get two solutions, positive 2 and negative 2. So our x-intercepts are at 2, 0 and negative 2, 0. Okay. As far as symmetry goes, remember this is an optional step, but symmetry does come into play here. If you plug in negative x for x, if you were to evaluate f of negative x, well, negative x squared is the same as positive x squared, because when we square it, the negative goes away. Same is true in the denominator, and so our function is going to be the same if we plug in negative x versus positive x. That means it is an even function, which means that it is symmetric about the y-axis. So we have y-axis symmetry. That means we're going to have a mirror image on the left-hand side and the right-hand side, which is great because that will help us make sure that when we're doing these calculations, we get everything right. If we don't end up with something like that, that puts up a red flag that we've made a mistake somewhere. All right. For asymptotes, remember we would have a vertical asymptote here if the denominator was ever 0, but we said that that can't happen, so there's going to be no vertical asymptotes, but there is going to be a horizontal asymptote. We have a rational function where the numerator and denominator have the same degree, and when that happens, we have a horizontal asymptote, y equals some number, and that number is the ratio of the leading coefficients. In this case, that's 1 over 1, which equals 1. An alternative way to see that is if you plug in larger and larger values of x, the function values are going to be getting closer and closer to 1. Same thing if we go in the negative direction. All right, so we've got a horizontal asymptote. For the intervals of increase and decrease and the local maximum and minimum values, we need to take the derivative. So let's do that now. I'm going to walk you through the first derivative, and then I'm going to let you do the second derivative on your own, just to make these videos a little bit shorter. But let's get a little bit of practice. We'll do the first derivative. Remember, when we're dealing with a rational function, we've got the quotient rule, and we've got that way of remembering the quotient rule, low d high minus high d low. So we've got the lower function, x squared plus 4, times the derivative of the higher function, which is 2x, minus the higher function, x squared minus 4, times the derivative of the lower function, which is also 2x, all over the lower function squared, x squared plus 4 squared. If we were to multiply everything out, if we were to distribute the two x's into each of these, we would get what? We've got 2x cubed plus 8x. And then over here, we have to distribute the 2x and the negative. So that's going to be minus 2x cubed, and then plus 8x, because a negative times a negative is a positive, all over that same denominator. And we do have a little bit of cancellation that happens. The positive and negative 2x cubes cancel, and then we can add those 8x's together, giving us 16x over the quantity x squared plus 4 squared. So that is our first derivative. We want to find the critical numbers, and the only critical number here is actually going to be 0, because that makes the numerator equal to 0. Denominator is never going to be equal to 0. It's always positive. So for our sign chart, the only critical number we have is 0. So we've got our factors on the left, 16x and x squared plus 4 squared. Well, anything squared can't be negative, so that's going to be positive on both of those intervals. 16x is going to be negative and then positive, and so that means our derivative, f prime of x, is going to be negative and then positive. So our function is decreasing and then increasing, and that gives us a local minimum at 0. And we know that the function value at 0 is 1 because we already found that the y-intercept was 0, 1. So we have a minimum at 0, 1. And yeah, that is good so far. Let's see. On our list, we've got the intervals of increase and decrease and the local maximum and minimum values. We just need the concavity and points of inflection. To save time, I am not going to go through and show the work for the second derivative. I would encourage you to pause the video and get practice working that out on your own. We would use the quotient rule again, and we end up getting 16 times 4 minus 3x squared all over x squared plus 4 cubed. And if we look at that, the critical numbers here, where the second derivative is equal to 0, happen at x equals plus or minus 2 over root 3. They come from setting this factor equal to 0. If we set it equal to 0, we add 3x to both sides, divide by 3, that gives us x squared is 4/3, take the square root, we get 2 over root 3, plus or minus. So those are going to be the numbers we have to deal with our sign chart for the second derivative. We've got 2 over root 3 and negative 2 over root 3. If we look at our factors, 16 is always positive. We will have to put some thought into 4 minus 3x squared, but then that denominator is also always going to be positive because x squared plus 4 is always positive. So we just have to look here at 4 minus 3x squared, and that is going to be negative, positive, and negative. It's positive in the middle because we can pick an example here, x equals 0, and when x is 0, this is positive. But when x is too big, then this ends up becoming negative because the 3x squared becomes larger than 4, so that becomes negative. And the same is true if x is too big in the negative direction. So we've got negative, positive, negative. That means that our second derivative is going to be negative, positive, negative. So we've got concave down, concave up, and concave down. And we do have inflection points at these values. Those are going to be important points, so we can plug those into the original function to find the function values there. So we can plot those inflection points. And whether you plug the positive one or the negative one in for your x value, The y value is going to be -1/2. So those are going to be our points of inflection. And now we are ready to sketch our graph. We have our y-intercept at 0, -1. We have our x-intercepts at ±2, 0. We have a horizontal asymptote at y = 1. So I'm going to draw that as a dashed line. And we have some points of inflection. 2/√3 is approximately equal to 1.15. It's a little bit more than 1. So we're going to have a point of inflection at about 1.15, -1/2. So that's going to be right around here. And the same thing with -1.15, -1/2. Let's talk about what's happening on each interval. We are decreasing all the way to 0, and then we are increasing afterwards. All right. And then our concavity is concave downward up until our first inflection point, and then upward in the middle, and then downward again. So all of that is going to help us sketch a graph. So let's start actually on the right-hand side. Let's take a look at this interval here. From 0 to 1, we are increasing and concave upward. Also remember, this is a local minimum. So we're going to be moving horizontally to the right at first, and then concave up. We're going to continue increasing, and we're concave downward. And also, we are asymptotically approaching this. So we're not going to go above, so it's just going to be approaching from the bottom. And then on the left-hand side, we can use all of these guidelines, but we also know that we have symmetry about the y-axis. So the left-hand side should be symmetric. Something like this. And then we can check here. Yes, it is decreasing on all of these, and then the concavity is still concave upward here, but concave downward there. And this ends up being our graph.